Welcome back, everyone. Okay, let's dive in. You sent us some really fascinating images, particularly of that Fourier GR1 humanoid.
Yeah, they're pretty striking.
And, we see robots walk around quite a bit now, navigating spaces. That's becoming almost commonplace. But what really caught my eye, and I think yours too, is the hands.
Absolutely.
The hands. I mean, not just simple grippers, but these multi-fingered hands doing complex, skillful things. Things we just, well, take for granted. It feels like a completely different level of challenge.
It absolutely is. That jump from just moving around or maybe a basic pick and place to what we'd call real dexterity, human-like dexterity. It's
Yeah.
huge.
Huge how. What makes it so much harder?
Well, think about just picking up something fragile, like say a grape, without crushing it, or juggling a couple of items, or using a tool, even turning a key.
Right.
These things need really fine coordination. They involve constantly changing contact with surfaces and controlling all those tiny movements across many joints. Doing that with a robot, that's where the complexity explodes.
And that leads us straight into the source material for today's deep dive. You shared this research paper with us, and it tackles exactly this problem head on.
That's right. It's all about training these humanoids, the ones with the complex hands, for dexterous manipulation. They're using reinforcement learning RL and leaning heavily on simulation, specifically that sim-to-real approach.
So the paper lays out what they call a recipe for this. Is that right? Like a set of steps to make this incredibly hard task maybe a bit more achievable.
Exactly, a recipe. It's a really good way to put it. A set of techniques, insights aimed at making this practical. So our plan today is to really unpack that recipe for you.
Okay.
We'll look at the core problems they face, why this is so difficult, and then we'll break down the specific methods they came up with, some of which are pretty novel.
All right, so think of this as your guide through their work. We're going to dig into the challenges, get into the technical weeds of their solutions, and hopefully you'll find some of the insights as surprising as we did. Because, honestly, getting a robot's hands to work like ours, it's a fascinating mix of engineering and AI puzzles.
Definitely. And to really get why it's such a puzzle, let's start by nailing down what dexterous manipulation actually means in this context. Like you said, it's way beyond a simple pincer grasp.
Right, it's about skill, isn't it?
Skill, precision, adapting on the fly, handling contact. It often means using multiple fingers together, maybe changing your grip pressure, or even coordinating both hands.
Like passing something from one hand to the other.
Exactly. That bimanual handover is a key example they tackle. Or lifting something big that needs two hands. You can see some of this in the paper's figures, like figure 1 and 3. It's about those subtle interactions.
Yeah, the way you might shift your grip slightly or use the edge of your finger. Stuff we do without thinking. Trying to teach a robot that seems incredibly hard. So they're using RL, reinforcement learning. We hear about RL succeeding in games, even in robot walking. Why does it struggle so much with this kind of fine-grained hand stuff on a complex humanoid?
Okay, so there are a few big reasons, and they all kind of tie together. The first massive one is just the sheer high dimensionality of the problem.
Meaning all the different joints and movements.
Exactly. Think about the robot itself. The Fourier GR1 has, what, 7 degrees of freedom in each arm, plus all the joints in those multi-fingered hands?
Lots of moving parts.
A lot. So if you just consider the position and maybe the speed of every single one of those joints, plus the state of whatever object it's holding, the number of possible states the system can be in is enormous, astronomical.
And then the actions, too, the commands you send.
Right. The action space is also incredibly high-dimensional because you can potentially control each joint independently. Trying to learn a good strategy, a good policy by exploring this gigantic state action space, it's computationally just overwhelming. A tiny change in one finger joint can totally change the outcome.
So mapping out all the possibilities the robot can be in and all the ways it can move, it's like trying to explore a space with millions, maybe billions of dimensions. No wonder random searching doesn't work well.
Precisely, and that leads into the second issue. These tasks are incredibly contact-rich.
Contact-rich. Okay, what does that mean practically?
Unlike walking, where contact is mostly predictable, feet on the ground manipulation involves constant, varied, often unpredictable contact, fingers touching the object maybe sliding on a table, different parts of the hand making contact, forces shifting.
Ah, I see. It's not just if contact happens, but how and where and how hard.
Exactly. Simulating those complex contact physics accurately is already hard. Then, getting an RL agent to learn policies that use that contact effectively, knowing just where to touch, how much force to apply, how friction will behave, that's even tougher. Tiny simulation errors can lead to big, real-world failures.
It's like all that physical intuition we have about how things feel, how they slip, how they balance.
Yeah.
The robot has to learn that from scratch, often from a simulation that isn't quite perfect.
You've got it. Then third, many of these manipulation tasks have long horizons.
Meaning they take a lot of steps to complete.
Right. Think about picking something up, turning it over, and placing it down carefully. Or that handover task, passing an object smoothly, involves a whole sequence of coordinated actions. In standard RL, the reward signal is often sparse.
Sparse meaning you only get rewarded at the very end.
Often, yes. You might only get a positive reward if the entire sequence is successful, maybe thousands of individual joint movements later.
And if you only find out if you succeeded way at the end, after maybe millions of attempts that fail somewhere along the way, how does the robot know which specific movements early on were good or bad?
That's the core problem with sparse rewards and long horizons. It's like trying to learn archery, but only being told if you hit the bullseye after shooting 100 arrows with no feedback on any individual shot. How do you improve?
You'd have almost no idea what to change.
Yeah,
Terrible feedback loop.
exactly. Without more frequent informative signals, the learning process is incredibly slow and inefficient, which brings us neatly to the fourth big challenge, the exploration problem.
Okay.
In this huge state space with tricky contacts and maybe only getting a reward occasionally after a long sequence, just randomly finding the right sequence of precise movements to even achieve one successful grasp, let alone the whole task, the odds are incredibly low.
It's like searching for a needle in a haystack the size of a continent. But the needle's also changing shape based on how you touch it. And you only get a thumbs up if you find it and assemble it perfectly from pieces scattered everywhere.
That's a pretty good, if slightly terrifying, analogy, yes. It's this combination of high dimensions, complex contact physics, sparse rewards, and the resulting difficulty of exploration that makes standard RL methods often fall short here.
So you really need something more tailored. You can't just throw a standard RL algorithm at it and expect magic.
Absolutely not. You need specific strategies to handle the simulation reality gap, guide the exploration, shape the rewards, and learn efficiently. And that's exactly what this paper's recipe aims to provide.
Okay, let's start unpacking that recipe. The first ingredient seems to address a classic problem, getting what you learn in simulation to actually work in the real world, bridging the sim-to-real gap. Why is simulation so critical here anyway? Why not just learn on the real robot?
Well, learning directly on the real hardware, especially for something this complex and contact-heavy, is just wildly impractical most of the time.
Why? Too slow?
Yeah,
Too dangerous?
both, really. It takes an enormous amount of time. You need millions, maybe billions of trials for the RL agent to learn. Doing that in real time would take forever. Plus, during all that exploration, the robot is going to fail a lot. It might drop things, hit things, damage itself or its environment.
Okay, yeah. Broken robots get expensive fast.
Very. And you need constant supervision. Simulation, on the other hand, lets you run things much faster than real time. You can run thousands or millions of attempts in parallel, resetting instantly after every failure, exploring potentially dangerous actions safely. It just gives you the scale and speed needed for RL. The paper mentions using NVIDIA Isaac Gym, which is built for exactly this kind of massive parallel simulation.
Right, running thousands of virtual robots side by side, learning 204/7. You just can't beat that efficiency.
Yeah.
But the simulation is never perfect, right? That's the catch.
That's the perennial catch, the sim-to-real gap. Policies that look amazing in the clean, predictable world of the simulator can just completely fall apart on the real robot with all its noise, imperfections, and slightly different physics.
And for dexterity, where tiny contact details matter, that gap must be even more problematic.
Hugely problematic. Tiny errors in how the simulator models friction or how stiff the joints are, or even just sensor noise differences, they can all add up. When you're relying on precise force control or delicate contact, these little discrepancies can make the learned policy totally useless in reality.
So how do people usually deal with this? Just tweak the simulation settings by hand until it looks sort of right.
Historically, yes, that's been a big part of it. A lot of manual tuning, often by engineers with deep expertise, trying to adjust simulation parameters, friction, damping, masses, motor models to get the sim to behave more like the real thing. It's tedious, time-consuming, and often feels more like an art than a science.
Sounds painful. And that's where this paper's first technique comes in, this automated robot tuning.
Exactly. This auto-tune module is their answer to that manual tuning nightmare. Instead of having an engineer sit there fiddling with sliders for weeks, they built a system to automate finding the best simulation parameters.
Okay, interesting. What kind of parameters does it actually tune? Is it just physics stuff?
It's pretty broad. It tunes key physics parameters within the simulator itself. Things like joint stiffness and damping, which affect how joints move and resist motion, armature, motor effort limits. Basically how the simulated motors and joints behave.
Right.
But it also tunes parameters in the robot's own digital model, the URDF file. Things like the inertia of the robot's links, how much they resist being moved, the precise limits of joint movement, even the exact positions and orientations of different parts relative to each other.
So it's trying to get both the simulated world's physics and the simulated robot's own properties to match reality.
Precisely. It's aligning both.
How does it figure out the right values? Does it need lots of real-world data?
That's the clever part. It needs surprisingly little real-world data. The core idea is this. First, you spin up lots of simulation instances in parallel, each one using a different random combination of the parameters you want to tune.
Okay, like trying out lots of different physics settings at once.
Exactly. Then, and this is key, you run a predefined set of simple movements called calibration sequences on the real robot. Just simple, controlled joint commands designed to see how the robot actually moves. And you only need to do this once.
Just one run on the real robot.
Just one run. You record the actual joint positions and velocities from that real run. Then, the auto-tune system compares how well each of those parallel simulations with their different parameter sets manage to track those same calibration commands.
So it sees which simulation's output most closely matched the real robot's output for the same input commands.
You got it. It measures the difference, usually using something like mean squared error, MSE, between the simulated joint trajectories and the real one.
And the simulation parameters that resulted in the lowest error, the closest match, are the ones you use for training the actual manipulation policy.
That's the winning set. Those parameters are deemed the best fit for the real robot's dynamics. The beauty is it's automated, leverages parallel simulation, and drastically cuts down that engineering time compared to manual tuning.
That sounds like a really significant practical improvement.
Yeah.
Did they actually show proof that this better tuning leads to policies that work better in the real world? Is there a direct link?
Yes, they did, and this is crucial. Table I in their paper shows a clear correlation. Lower MSE values from the auto-tune process, meaning the simulation better matched the real robot, directly corresponded to higher sim-to-real transfer success rates for the policies trained using those parameters.
So better sim fidelity, found automatically, genuinely translates to more successful robots in reality. That's compelling.
It really is. It validates the whole approach. And another interesting point you raised earlier, they showed this wasn't just tied to the Fourier hands they primarily use.
Oh, yeah, you mentioned it worked on different hands.
Right. In their videos, they demonstrated that policies trained using parameters found by this auto-tune system could transfer successfully not just to the Fourier hands, but also when they swapped in different hands, Inspire hands, which have different mechanics, different mass, different actuation patterns.
That suggests the auto-tuning method itself is quite robust and potentially generalizable across different hardware. Big plus.
Definitely. It's a strong piece of their sim-to-real puzzle.
Okay, so that's handling the robot side of the simulation, getting its dynamics right automatically. What about the other side? The objects it interacts with, real-world objects are incredibly varied. How do you simulate that messiness?
That's the second big challenge in modeling the environment accurately. You're right, the variety is endless. Look at the objects they tested with simple blocks, yes, but also sauce bottles, cups, a Rubik's Cube, even grapes, cans. All different shapes, sizes, weights, textures, friction properties.
Trying to make perfect 3D models and physics models for every possible object seems impossible, right? And totally limits the robot to only things you've pre-modeled.
Exactly. It doesn't scale and it doesn't allow for handling novelty. So their approach here is actually quite interesting, maybe even counterintuitive. They don't try to create super detailed, accurate models of specific real-world objects in the simulation. Instead, they use very simple, approximate geometric primitive shapes.
Like cylinders, cubes, spheres. That basic.
That basic. But,
Yeah.
and this is the absolutely critical part, They heavily randomized the parameters of these simple shapes during training.
Randomize what?
Things like their color, their size within a range, their mass, and crucially, their friction coefficients. So the robot might interact with thousands of slightly different cylinders, cubes, and spheres, all with varying physical properties.
Hang on. You're telling me they trained the robot to pick up, say, a randomized simulated cylinder, and that skill somehow lets it pick up a real-world, unseen object, like a can of soup or a bottle of ketchup. That feels backwards. Why wouldn't a more accurate simulation be better?
It does feel backwards, but their results suggest otherwise. They actually found, as shown in Figure 4, left, that training policies on complex, detailed object models was less sample efficient in simulation. It took longer to learn.
Slower with better models. Weird.
Right. Whereas training with these simple, randomized primitive shapes was more sample efficient, the policies learned faster in sim. And the really key finding, these policies trained on simple, randomized shapes generalized surprisingly well to a whole range of unseen real-world objects. They achieved zero-shot transfer.
Wow. Okay, that is surprising. So the thinking must be, by forcing the robot to deal with constant variations in basic physics like mass and friction, even on a simple shape, it learns more fundamental manipulation skills, skills that aren't tied to one specific object geometry.
That seems to be exactly the idea. You're training the policy to understand the core physics of interaction, how to adjust grip force for different weights, how to handle different friction, how to compensate for size variations rather than overfitting to the visual details of one specific 3D model.
So the simplicity of the shape actually helps because it makes it easier to randomize the underlying physics more effectively.
Precisely. It allows for broader domain randomization over those crucial physical properties, which appears more important for achieving robust, generalizable dexterity than getting every visual detail perfect. It's a really powerful argument for focusing on the physics of interaction.
Okay, that's a fascinating insight. So, ingredient one of the recipe, auto-tune the robot model and use simple randomized primitive shapes for objects. That gives you a more robust simulation setup. What's the next big challenge they tackled in their recipe?
The second major challenge, even if your simulation is pretty good, is actually guiding the robot's behavior. How do you tell it what to do effectively? We already talked about the sparse reward problem.
Right, just rewarding the final success isn't enough guidance, especially for long, complex tasks like passing an object hand to hand.
Exactly. And traditionally, crafting reward functions often involves a lot of manual, task-specific engineering, carefully shaping the reward to encourage intermediate steps. The paper points out that sometimes the RL community kind of assumes the reward function is just given, but for complex robotics, designing a good reward is a huge part of the problem itself.
Yeah, if you need a PhD student to spend weeks designing a custom reward for every single new skill you want the robot to learn, that's not going to scale very well.
Not at all. So their core idea here is to structure the learning around achieving sequences of intermediate goals, specifically breaking tasks down into interleaving contact goals and object goals.
Okay, contact goals and object goals. Let's unpack that. What's a contact goal?
A contact goal is about defining how the robot should be interacting with the object physically. Not just touch it, but where on the object should the fingers make contact? What kind of grasp posture are we aiming for? For instance, to get a stable lift, you might want fingertips applying force at specific opposing points.
Got it. So it's about the desired state of the robot-object interaction itself and object goals.
Object goals are simpler to understand. They define the desired state of the object at certain points. Where should the object be in space? What orientation should it have? For a lifting task, an object goal might be get the object to this height. For the handover, it might be get the object to this specific position relative to the receiving hand.
So instead of one big reward at the end, you're providing a series of smaller targets along the way, focused on both how the robot touches the object and where the object ends up.
Exactly. And they have a neat technical way to specify those contact goals that's quite clever and scalable. Key point-based contact goals.
Seed points, like specific points in space.
Sort of. They generate what they call contact stickers. These are essentially target points or small target regions generated procedurally on the surface of a simulated object. These stickers represent good places for the robot's fingertips to make contact.
Contact stickers. I like that. So you're putting virtual sticky notes on the simulated object saying, aim your fingers here.
That's a great way to visualize it. The reward function then simply encourages the robot to minimize the distance between its actual fingertip positions and the locations of these designated contact stickers. Equations 1 and 2 in the paper formalize this distance calculation.
So you're guiding the grasp shape by rewarding proximity to these strategically placed virtual targets.
Precisely. And by placing these markers differently, you can guide the robot towards different types of grasps or contact patterns without needing complex reward terms based on measuring forces or anything like that.
And they showed this worked, right? I think Figure 5 demonstrated that changing where they put these stickers on a simulated box
Mhm.
actually resulted in the robot learning different ways to lift it. Like sometimes it pinched, sometimes it cradled.
Exactly. It showed that this relatively simple mechanism, just defining target contact points, can effectively shape the emergent behavior. It allows you to encode some human intuition about good contact points.
And the generalizability comes from.
The generalizability comes from using the same principle, breaking tasks into contact goals, defined by stickers, and object goals across different tasks. Whether it's grasping, lifting, or handover, you apply the same fundamental reward structure. You just change the specific locations of the stickers and the target object states. You don't have to reinvent the reward system from scratch for every new skill.
Okay, so structured goal-based rewards using these contact stickers offer a more systematic and general way to guide the learning. That makes sense. But we still have that massive exploration problem, right? Even with better rewards, finding those rewarding states, even the intermediate ones, in such a high-dimensional space where precise control is needed, that still sounds incredibly hard. How do they make the learning itself more efficient? That's challenge 3.
Absolutely. Sample efficiency is key to making this practical. They hit this with two main techniques. The first one is really interesting, task-aware hand pose initialization.
Task-aware initialization that involve using human demonstrations.
Yes, but in a very minimal and clever way. It's quite different from traditional imitation learning, where you might need an expert human to perform the entire task perfectly, maybe hundreds of times, to create a data set.
That sounds laborious and expensive.
It really is. And getting perfect teleoperated demonstrations for complex dexterous tasks is hard in itself. This paper avoids that heavy lifting. Instead, they just have a human play around with the robot hands and objects in the simulator for a very short time.
Play around, like just moving the hands near the objects.
Pretty much. They state it's less than 30 seconds of human teleoperation per task. The human isn't necessarily completing the task perfectly, just interacting in a way that's relevant, putting the hands near the object, maybe trying a grasp, moving the object a bit.
Wait, just 30 seconds of messing around in sim? That's it?
Yeah.
Compared to hours of expert demos.
Exactly. It's incredibly low effort. But here's the key. They collect the robot and object states, joint positions, object poses, encountered during that brief interaction. Then, when they start the actual RL training episodes, instead of always starting the robot from some default or totally random pose.
Ah, they started from one of those states the human briefly visited.
Precisely. They randomly sample initial states for the RL agent from this pool of human-generated near-miss or relevant states.
So the human isn't showing this solution, just giving the RL agent better starting points for its own exploration, like putting it in the right ballpark to begin with.
That's exactly the idea. It dramatically biases the exploration towards regions of the state space where successful interactions are more likely to occur. It gives the agent a much better chance of stumbling upon those sparse rewards early on.
Does it make a big difference in practice?
A huge difference, according to their results in Table 2. For a standard grasp and reach task, using this human prior initialization boosted the percentage of successfully trained policies from 60% to 80%.
Okay, that's a solid improvement.
But for the really complex bimanual handover task, the impact was massive. Without initialization, they had a 0% success rate in training a working policy. With this simple 30-second initialization, they got up to a 30% success rate.
Wow, from 0 to 30% just by giving it slightly better starting positions.
Yeah.
That's incredible. It suggests this minimal guidance can unlock tasks that were previously completely intractable for RL to solve on its own.
It really highlights how powerful even a tiny bit of relevant human prior can be for jump-starting exploration in these incredibly hard problems. It's a big efficiency game.
That's a great takeaway. Okay, what was the second technique for learning efficiency?
The second technique is divide and conquer distillation. This is aimed at tackling tasks that are complex because they involve multiple stages or multiple objects.
Like breaking a big problem into smaller, easier ones.
Exactly. So imagine a task where the robot needs to grasp and move several different objects. Instead of trying to train one single policy to do everything from scratch, you first train simpler specialist policies.
A specialist for each object, maybe.
That's one way, yes. You could train one specialist just to handle object A, another for object B, and so on. These subtasks are usually much easier to learn. Once you have these specialist policies working well,
You use them somehow.
you use them to generate lots of successful example trajectories in simulation. So the specialist for object A performs its task many times successfully. The specialist for object B does the same. You collect all this expert data generated by your specialists.
Okay, so you have a data set of success generated automatically by the simpler policies.
Right. Then you train your final generalist policy, the one you want to handle the full complex task using this data set. It's basically learning by imitating the successful behaviors of the specialist. This process is called distillation.
So you turn a hard exploration problem for the generalist into more of a supervised learning problem, using the specialists as teachers.
That's a great way to put it. It leverages the fact that learning from successful examples is often much easier and faster than discovering those successes through pure exploration, especially for complex tasks.
Did they look at different ways to break down the task, like how you define the specialists?
Yes, they did an interesting ablation study on this, shown in Figure 4, right? For a multi-object task, they compared a few strategies, training one policy on all objects right away, training specialists where each one handled objects of a similar geometric shape, training specialists where each handled a mix of different shapes, and training specialists where each handled only a single specific object.
Lysol. Lots of options.
Yep.
How do they compare in terms of learning speed in the simulation?
Well, as you might guess, training the specialists on just a single object each single was the fastest in simulation. Those policies learned their simple tasks very quickly. The shape and all strategies were slower, and interestingly, the mix strategy where specialists handled a mix of shapes was actually the least sample efficient in simulation. It took the longest to converge.
Okay, so single specialists learn fastest in sim, mix specialists learn slowest. That seems intuitive. Simpler tasks are faster to learn. But does that speed translate to better performance in the real world?
Now here comes another really surprising, counterintuitive result. This is one of the paper's key insights regarding sim to real. When they took the final generalist policies trained using these different distillation methods and tested them in the real world.
Results flipped.
Completely. The mix policy, the one that was slowest to train in simulation, achieved the highest real-world success rate, 90% on unseen objects.
90%, wow. Any others?
The single policy, the fastest learner in sim, only managed 40% success in the real world, and the all policy was even lower, around 23%.
That's a massive difference. So the way you break down the problem for the specialist dramatically affects how well the final policy generalizes to reality, even if it makes simulation training seem slower.
Exactly. It's a critical finding. The mix approach, while taking longer in sim, seems to force the specialists, and thus the final policy, to learn more robust, generalizable strategies that can handle variations across different object types.
Whereas the single specialist might have overfitted too much to their one specific object, making them brittle when faced with real-world variations.
That's the likely hypothesis. The mix strategy seems to hit a sweet spot. It gets the benefits of breaking the problem down, but the mixing within the subtasks promotes better generalization, leading to much better real-world outcomes, even at the cost of simulation speed.
That really underscores that optimizing purely for simulation performance isn't always the right goal for sim-to-real robotics. Fascinating.
It absolutely does. It shows there are subtleties in how you structure the learning process itself that significantly impact real-world transfer.
Okay, so we've got better simulation through auto-tuning and randomized primitives, better guidance through goal-based rewards and contact stickers, and more efficient learning through minimal human initialization and this clever divide and conquer distillation. What's the final piece of the puzzle the robot needs to see, right? Vision.
Right. Challenge number 4, seeing the world. How do you use visual input, like camera images, to drive these manipulation policies? And critically, how do you make sure that vision-based policy transfers from the simulated camera view to the real camera view?
Yeah, the perception gap. That seems like another big hurdle. Simulators look clean, the real world is messy, lighting changes, textures are different.
Exactly. Transferring policies learned from raw pixel data, especially something like RGB color images, is notoriously hard because of that gap. Even depth images, which capture geometry, can differ significantly between sim and real due to sensor noise, calibration errors, lighting effects on the sensor.
So relying purely on, say, the robot's head camera seems risky for sim to real. How did they handle this vision challenge?
Their approach was to not rely on just one type of visual input. They used a mixture of object representations, combining both sparse, robust information with denser, more detailed information.
Sparse and dense. What's the distinction here?
Okay, so the sparse information is low-dimensional, high-level data about the object that's relatively robust to visual noise or appearance changes. In their case, they use the object's approximate 3D position, basically. It's XYZ coordinates in space, like its center of mass.
Just knowing where the object is, broadly speaking.
Right. A very fundamental piece of information for any manipulation task. It's low-dimensional, but highly relevant.
How did they get that 3D position reliably in the real world? Especially if the robot's own hand might be blocking the view from its head camera sometimes.
Good question. They anticipated that occlusion issue. To get a robust 3D position, they used a third-view camera, a camera set up on a tripod, looking at the workspace from the outside, not mounted on the robot.
An external viewpoint that always sees the scene.
Exactly. They used an Intel RealSense depth camera there. To actually identify the object and estimate its position, they combined the depth data with image segmentation using a powerful vision model, SAM2, the segment anything a model to.
So SAM2 draws a box around the object in the image, and then they use the depth data within that box to figure out its 3D location.
Roughly, yes. It gives them a pretty stable estimate of the object's center of mass, even if the scene is a bit cluttered or the robot's hand is nearby.
Okay, so that's the robust, sparse 3D position from the external camera. What's the dense information?
The dense information comes from the camera the robot does have on its head, an egocentric depth image. This gives the robot a much richer, higher resolution view of the object's shape and the immediate surroundings, right from its own perspective.
So this is for the fine details needed for grasping, seeing the curves and edges up close.
Exactly. This detailed geometric information is crucial for actually performing the dexterous parts of the task, like positioning fingers accurately relative to the object surface. But, as we said, this kind of dense, pixel-level data is more vulnerable to the sim-to-real gap.
So the policy gets both inputs. The general, where is it, from the outside camera, and the detailed, what does it look like up close, from its own head camera.
That's the strategy. Give it both the robust grounding signal and the detailed view needed for dexterity. And they showed in Table 3 that this combination works significantly better.
How so?
Policies trained using both the egocentric depth and the 3D position, depth plus pose, had considerably higher success rates in transferring to the real world compared to policies trained using only the egocentric depth only.
And the difference was bigger for tasks needing more precise interaction?
Yes, exactly. Which really supports the idea that the sparse 3D position helps anchor the policy and makes it robust enough to transfer, while the dense depth provides the necessary detail for the actual manipulation skill itself. It's a smart combination.
Makes sense. Did they also use other standard tricks to make the vision more robust beyond just mixing inputs?
Oh yes, absolutely. They relied heavily on standard domain randomization techniques as well. You still need that.
Like randomizing textures and lighting in the simulator?
That and much more. They randomized object properties extensively: mass, friction, scale, starting position. But they also randomized things about the robot and the sensors in simulation.
Like what?
Things like the friction in the robot's own hand joints, the gains of the low-level PD controllers that execute joint commands.
Why randomize controller gains?
To make the policy robust to small variations in how the real robot's motors actually respond, they also added random forces acting on the robot and object, added noise to the sensor observations like the camera images and joint readings, and even added artificial delays or lag between observations and actions.
So basically making the simulation less perfect and predictable in lots of different ways.
Exactly. Table 4 in their appendix lists all the things they randomized. The goal is to force the policy to learn strategies that don't rely on perfect sensing or perfect control, making it much more likely to cope with the inevitable imperfections and unexpected things that happen in the real world.
Okay, so the vision recipe is mix robust, sparse 3D position with detailed, dense, egocentric depth, and then layer on top a whole lot of domain randomization for everything from physics to control noise.
That pretty much covers the fourth key part of their technical recipe.
All right, so now we have all four pieces: automated simulation tuning, goal-based rewards, efficient learning strategies, and robust vision. Let's step back and look at the big picture. What did applying this whole recipe actually allow them to achieve on the real Fourier GR1 robot? What were the demonstrated capabilities?
Well, the results were quite impressive. They successfully trained and deployed policies that could perform not just single-hand tasks like grasp and reach, but also those more complex bimanual tasks.
Like the box lift and the handover.
Exactly. Lifting a large box requiring both hands and successfully passing an object from one hand to the other. Getting that kind of coordination between two multi-fingered hands is a significant step, as shown in their figure 3.
And we talked about generalization. How did that pan out in the real-world tests?
The generalization was strong on two fronts. First, as we discussed, they achieved zero-shot generalization to a pretty wide array of unseen real-world objects. That's shown nicely in Figure 1. Policies trained only on those simple, randomized shapes in Sim could pick up and manipulate real objects with totally different shapes, weights, and appearances. Household items, different containers, 3D prints things they'd never encountered.
That zero-shot capability is really key, right?
Yeah.
It suggests the robot learns something fundamental about interaction, not just memorize specific objects.
It really does. And the second aspect of generalization was transfer across hardware, successfully deploying policies trained using their framework onto the Inspire hands, which are physically different from the Fourier hands.
So generalization across objects and even across robot hands. What about handling disturbances? The real world isn't static.
Right. They tested for robustness. During real-world task execution, they actually perturbed the robot or the object it was holding. They pushed it, pulled it, knocked it, dragged it. Figure 6 shows examples. The learned policies were generally able to withstand these disturbances, maintain their grasp, regain stability, and continue with the task.
That's crucial for any practical application. Robots need to be able to handle bumps and unexpected forces.
Definitely. And one last point on capability they showed. These learned RL policies aren't just standalone skills. They can be integrated into larger systems. They built a simple pick-and-drop routine using a finite state machine that called their learned grasp and reach policy as a component. It shows the learned skills can be building blocks for more complex behaviors.
Okay, so summing up the achievements. Complex bimanual tasks, impressive zero-shot generalization to unseen objects in different hardware, robustness to physical disturbances, and integration into larger systems. That feels like a solid package.
It really is. It presents this comprehensive practical framework, their recipe, that demonstrably works for training complex dexterous skills on real humanoids using RL and vision, and importantly, doing so without needing exhaustive, task-specific human demonstrations for every little thing.
It definitely lays out a clearer path forward for making this kind of advanced manipulation more scalable and achievable on these complex robot platforms.
And for anyone listening who's interested in the future of robotics or automation, understanding these core techniques, how to tackle sim to real, how to design rewards that scale, how to make learning efficient, how to handle perception, these are really the foundational challenges being solved right now at the cutting edge.
But, as always in research, progress also highlights what's still difficult. The paper was also quite clear about the remaining limitations, right? What did they identify as the big hurdles still ahead?
Yes, they were very realistic about that. The main point they stressed is that while this is progress, it's still nowhere near true human-level general-purpose manipulation.
We can pick up almost anything, use tools in incredibly flexible ways. Robots are still very far from that.
Very far. Our dexterity is just on another level, so this is a step, but a long road remains.
Did they point to specific parts of their own recipe that need more work?
They mentioned reward design as one area. While their goal-based approach is more general than old-school reward shaping, they speculated that incorporating even richer human priors might be beneficial. Perhaps using more complete, albeit imperfect, teleoperated demonstrations could teach the robot more subtle aspects of a task than just defining goal states and contact points.
So maybe finding a middle ground between their minimal initialization and full imitation learning.
Potentially, yes. Finding the right way to inject human knowledge effectively is still an open question. They also highlighted the persistent challenge of the dynamics sim-to-real gap.
Even with their auto-tuning.
The auto-tuning helped match the robot's own dynamics. But accurately simulating the physics of complex dynamic interactions, like the forces and momentum exchange during that fast-paced handover task, is still extremely difficult. They suspect this remaining gap in interaction dynamics simulation might be why the handover task had a lower real-world success rate compared to simpler grasps. Standard domain randomization might not be enough for these highly dynamic context situations.
Okay. So simulating the robot itself is one challenge. Simulating the complex physics between the robot and dynamic objects is another, possibly harder one.
It seems so. It's a known bottleneck in the field. And finally, they pointed to a really fundamental limitation, one that might not be solvable just with better software or algorithms. The hardware itself.
The robot hands.
Exactly, the physical hands. While the Fourier and Inspire hands are multi-fingered and quite advanced for robots, they still have far fewer actively controlled joints, far less dexterity than a human hand.
We have something like 20 plus degrees of freedom in our hands. How many do these robot hands have?
The Fourier hand has 6 actively actuated degrees of freedom, plus 5 underactuated ones that move passively. The Inspire has 6 active and 6 passive, so significantly fewer independent control dimensions than a human hand.
Right.
Their point was that their learning framework might actually be capable of learning more dexterous behaviors than the current hardware can physically execute. The bottleneck might be shifting from the learning algorithms to the physical capabilities of the hands themselves.
That's a critical point. You could have the smartest AI, but if the robot physically can't make the necessary fine movements, it doesn't matter. The hardware limits the ceiling of achievable dexterity.
Precisely. They see developing more sophisticated, more highly articulated robot hands as a crucial next step for the field to unlock truly human-like manipulation.
Okay, so let's recap their full recipe one last time. It's automated tuning for the robot model plus simple randomized primitives for objects to get simulation right. Goal-based rewards using contact stickers for scalable guidance. Efficient learning via minimal human initialization and divide-and-conquer distillation. And robust vision using mixed sparsedance inputs plus heavy domain randomization.
And putting that all together led to successes in bimanual tasks, zero-shot generalization, robustness, and integration potential.
It's definitely a compelling package, showing a practical route towards more capable humanoid manipulation using RL and vision, without needing a prohibitive amount of human demonstration data for every single skill.
And understanding these pieces, the sim-to-real battle, reward design, exploration, perception, really gets you to the heart of the challenges in modern robotics.
Which brings us to that final thought, building on those limitations. They highlighted the hardware, the hands themselves, as a potential bottleneck now, and the dynamics gap for complex interactions remains tough. So, here's something for you, the listener, to ponder. If we could solve the hardware problem, if we could build robot hands with truly human-like physical dexterity, what then becomes the single biggest remaining hurdle to achieving general purpose, human-level manipulation? Would the current software approaches, like the ones in this recipe, be enough? Or would we fundamentally need new breakthroughs in AI, maybe in how robots learn physics intuitively, or perhaps even completely different learning paradigms altogether?
That really is the big question looming over the field, isn't it? Even with perfect hands, is there still some secret sauce to human dexterity, maybe in our perception, our internal models, or our learning process that current AI hasn't captured yet?
Definitely food for thought. We'll have to leave it there for this deep dive.